A long time ago, before GPUs, before multi-core processors and gigabytes of RAM, clever algorithms were the only way to render complex graphics in real time. Those algorithms are now mostly forgotten, as nobody needs them or is interested in them. Well, almost nobody. I like to reverse engineer the clever tricks programmers of that era were using, and I was one of them. I hope you'll follow me on this exploration. In this video, I'm going to show you algorithms that solve the seemingly simple task of drawing a circle, and will do so with very strong constraints on the operations we're allowed to use. In the early days of video games, the late 70s and early 80s, the processors in home computers and game consoles were mostly 8-bit processors such as the 6502 and the Z80. Those processors were not only slow by today's standards, with frequencies around 1 or 2 MHz and no parallel execution of any kind, they had very limited instruction sets, without multiplication and division operations, with only support for integer numbers and no floating point numbers. That doesn't mean that multiplications were impossible, just that they were very, very expensive. Imagine if you had to do all your multiplications by hand. As a consequence, algorithms avoiding them were preferable. Operations that 8-bit processors were very good at running fast because they were implemented with few simple logic gates include additions and bit shifting. So that's what we're going to use. The way mathematicians would commonly describe circles is often with equations such as x squared plus y squared equals r squared. Or you can also use a system of equations with some trigonometry added. X equals r times the cosine of theta, and y equals r times the sine of theta, where if you draw a crude circle like that, with here the angle theta, this distance here is the radius of the circle, and this equation describes what happens when you walk the circle, changing theta as you go. Very simple. So the first thing we can notice is that this equation here is quadratic. So everything in there, once differentiated, will become linear, because the differentiation of something of degree 2 is something of degree 1. And degree 1 is very easy, it's additions. Okay, so let's keep that differentiation idea, but let's look at this one and see what happens when we differentiate it. So when we differentiate that, well, on theta, so like we try to see what happens when we move by a very small variation of the angle theta here. So what happens? So r stays the same. Cosine of theta, the derivation is minus sine. So we obtain this equation. dx equals minus r times sine of theta times the difference in theta. And same thing for y, except that the derivation of sine is cosine without an extra sign, and we have that. And now we can notice something. This here is x, and this here is y. So we can rewrite that same thing, and we obtain the very simple equations. dx equals minus y d theta, and dy equals x d theta. And that's very easy, because we know now that we can, if this guy here is something very small, we can make the multiplication very easy. What we'll use is the simple trick, which is that, let's say we have something very small, but that's the inverse of a power of 2. Why is that easy? Because multiplicating by this in binary means shifting the bits to the right. So let's say, for example, you have a binary sequence that is that, for example. But it's x29. Yeah. So if we shift this one bit to the left, we get 1, 0, 0, 16, 20, which is 41 divided by 2, rounded down. So yeah, this is how you divide by 2 to the nth. So if we choose a value by which we change our angle that is an inverse power of 2, then multiplying any number by it is just shifting it to the right by n. So we still have the problem of determining the value of n, but we only have to do it once per circle, so this is not really a hot path. And all you have to do is shift 1 to the left until you run over r. Why? Because we want a circle that is continuous, so we never want the variations of y and x to go over 1. We need 2 to the nth to be just a little more than r. And this way, when we divide anything that is smaller than r, which all the points on the circle are, we are just going to get something that is a little less than 1 pixel. So there is the additional complexity here that we need to work on fixed point numbers, because we need something that rounds correctly. So that's a weakness of this algorithm. We need to work with larger numbers than just, coordinates on the screen. Here is a working algorithm. So this is how we determine the value of n, which, by the way, is the simplest way to get logarithm of base 2. And then we can just walk the circle by adding to t, which stands for theta here, starting with 0, and every time we just add to x, well, we remove to x y shifted n times to the right, and we add to y x shifted n times to the right again, and that works. That gives us, here is a circle that has been drawn by that algorithm, which works well, but we can do better. Imagine we want to walk the circle, so let's say we have a large circle like that, and we want to walk this circle, so we start from this point, let's say. And one thing we can do is walk to the right, and walk and walk and walk and walk until we reach the circle. And I'll get to how we do that in a minute. And when we hit the circle, or when we go past the circle, what we can do is take one step to our right, which was the bottom here, and do that again. And again. Until we are done drawing the circle. So, in order to do that, we need to know when we go past the circle. And we do that using a discriminating function. What is a discriminating function? It's a function of the coordinates that evaluates as always positive outside of the circle, always negative inside of the circle, and 0 when on the circle. It's very easy to build such a function for a circle. We can use the first equation that we wrote at the beginning and just use that by just putting the r on the other side here. And we can check, it's easy to see that this is 0 when we are on the circle. When we are outside the circle, let's say we start from a point on the circle and we go 1 extra x here. What is it going to do? Well, this is going to be more than R2, and so this is going to be positive here. If we go with a coordinate that is smaller than our point that was on the circle, then this gets smaller, and we are below R2, and this way the function will get negative. Okay, so if we plot the function, it looks like this. So it may seem like computing the value of this function for each point where we try to walk is going to be expensive, because we've got multiplications here. So that's going to be tricky. We can do that, but here's the trick. Again, use that differentiating idea, but with a 1 pixel difference. So let's say we want to know what happens when we walk 1 pixel to the right. So 1 pixel to the right would be x plus 1 and y. So let's try that. That's x plus 1 squared plus y squared minus r squared. And we can develop this. This is x squared plus 2x plus 1, and then y squared minus r squared. And here we can notice that this plus this minus this, that's our differentiating function. So we group those terms here, replace them by f of x and y, and what do we have left? 2 times x plus 1. And this is wonderful, because this is a multiplication, but it doesn't count. As we've seen, multiplying by 2 is just shifting to the left, and adding 1 is easy. Wonderful. That means that if we know the value of f for 1 pixel, we know the value of f for all the pixels to its right, using only operations that are 1 shift, 1 add. And it's not even any add, it's add 1, which is particularly easy to do for old computers. They have dedicated instructions for that. This is in here, we have 1 add. Let's do 6502 operations. This is rotation to the left, and this is increment A. Okay, so now we just have to do the same thing for, 1 step to the right, or 1 step down. So f of x and y minus 1, our coordinates here are x, y. So on an actual screen it might be reversed, but let's ignore that for the moment. That's a simple symmetry. Alright, so that's x squared plus y minus 1 squared minus r squared. And that's x squared plus y squared minus 2y plus 1 minus r squared. And again, we find this term, and this term are just the value of f for x and y. So what we have left is f of x and y minus 2y plus 1. And again, those are only simple operations. This is a regular subtraction. This here is a rotation to the left, and this here is an increment. So additions and shifts. And that's it, we have our algorithm. So here is an implementation. All we have to do is start at one specific point of the circle. So let's say we start with this point here. So that's coordinates 0 and r. And for this point, f is also easy to calculate. It's just minus r, it's 0. Of course, because the point is on the circle. Usually you want to start with a pixel that is just 1 down. So you want 0, that's 0 r. We want to start with 0 r minus 1. And the reason for that is that if we start with a point that is on the circle, we are immediately going to have to go down, and that will make something that looks like that, and your circle is going to appear a little pointy. It will have one extra point here. Whereas if we start just below, it's going to smooth things out. Trust me. We can also do half a we can also do half a pixel down. which is even better. That's 0 plus r squared minus r plus 1/4 minus r squared. And those go away, and we are left with minus r plus 1/4. 1/4 is less than 1, so we can round it out. And that's just minus r. So this is very easy. Our first value of f for a pixel that is just somewhere half pixel down. And that's a good value to start with. And we are just going to compute variations from that value. So here we start with x equals 0, y equals r, and we start with a value of minus r. And that's going to be actually a pretty good circle. The circle that it draws looks like that, and that looks perfect. Okay, so what it does is that while we've not drawn the whole circle, we walk one to the right, so x plus plus, and we change f accordingly. Then if f becomes positive, so if we've walked out of the circle, then we do one step down, and that's y minus minus, so we decrement y and we change f accordingly, and we continue doing that, and that's it. That's all there is to it. This very simple algorithm that uses only additions and shifts is actually drawing a circle. This is going to be our center. I'm going to keep track of the values of f here on the side, x and y. So let's start with 1, 2, 3, 4, 5, 6, 7, 8. Let's do 8. So we start with this point. So we're just going to color that. So x equals 0, y equals 8. And f equals minus r, which is, so 1, 2, 3, 4, 5, 6, 7, 8. So minus 8. That's our starting value for f. Alright, so we walk one pixel to the right. Oh, and also we draw all the symmetries. So this guy down is 1, 2, 3, 4, 5, 6, 7, 8. So we have this guy here. And then we can draw all the symmetries here, and we also have 1, 2, 3, 4, 5, 6, 7, 8. This guy, this guy, this guy, and 1, 2, 3, 4, 5, 6, 7, 8. And this guy, and this guy. Alright, so new value here is, so x equals 1, y is still 8, and f is now equal to, so we need to add, because we walk to the right, we need to add 1. Let's check our notes here. So 1 plus 2x. So 2x is 2, plus 1, that's 3. So we add 3, and we end up with minus 5. That's still negative, so we'll continue working to the right. So color this dot and all its friends here, all the symmetries as we go, without having to compute anything for these points. So that's 2, 8, and 2 times x, that's 4, plus 1, that's 5, and we're at 0. So we hit the circle. We're actually right on the circle here. So we are not yet over, so we'll continue. So one more step to the right. And now 3, 8, and 2 times 3, 6, plus 7, plus 1, 7. So now we are way over. So now it's time to go down 1 pixel. Okay, so stage 3, this is 7, and now our formula for one step down is 1 minus 2 times y. So 1 minus 14, so that's minus 13 that we need to remove, to add to f. So minus 6, and we are back inside of the circle now, meaning that we walk to the right. All right, so that's 4, 7, and 2 times 4, 8, plus 1, 9. So we add 9, and that's 3. We went out of the circle again. So one step down. Starting to look like a circle. One step down, that means 4, 6, and 1 minus 2 times y, so 1 minus 12, so that's minus 11. So we remove 11 from that, and we are left with minus 8. So we are back inside the circle, so we walk to the right. And we're almost done here. So to the right, 5, 6, 2 times 5, 10, 11, so we add back 11, we are out of the circle, and so that means we move down here, here, and here, and we are going to draw those pixels actually, sorry, those pixels, not this one, bad, twice. We're going to draw that pixel twice because it's symmetrical, but that's fine. Implementing the logic node 2 would actually take more time. And yeah, so that's 5, 5, and now x is now superior or equal to y, so we know that we should stop, and we're done. We've drawn a circle. So because it's a small circle, I mean, it doesn't look that circle-ish, does not look that smooth. You can do the same thing if you want with a larger circle. You don't even need to compute f here because we are at the stop here. So that thing actually doesn't. See? That's our circle. We can actually do the same thing in assembly language on a vintage computer. So I'm using here the 8-bit workshop, which has an emulator for an Atari computer that is using a 6502 processor, and this is the implementation of the same algorithm written in assembly language for the 6502, and it's drawing this circle here to the right. This is the actual emulator running this code that you can see here. So I'm not going to go into too much detail in there. You would have to learn 6502 assembly if you don't know it already, so that's probably a little overkill. It would do the same thing that we've done on paper anyway. And that's it. This is how you draw a circle using additions and shifts. I have nothing more. We're done here. Bye. You can go somewhere else, or you can do the usual thing if you want to. I don't necessarily want you to. It's fine. Do what I'm not telling you what to do.